Greetings, everybody. Hey, we're on chapter 8, the family of stars. So we're going to actually start talking about stars and how they work a little bit. This is basically a chapter about star data. And what we're looking at here, by the way, this is a star cluster. Stars tend to form together because they originate in large clouds of gas and dust. The clouds can be much larger. They can be light years across, much larger than any planetary system. And they collapse down, and as they collapse down, they get hot, and stars begin to form. We'll talk more about that as we go along. Now, the first thing, remember the most important, most fundamentally important thing in all of astronomy is scale. And scale translates to things like sizes and distances. So the most fundamental thing we can know about anything really is how far away it is from us. And that's what we're going to talk about here. This is the initial technique that was actually used. It's called parallax. And this technique is infallible. Let me show you how it works real quick. Here's the sun. Here's the Earth going around its orbit every 12 months around the sun. And from the Earth to the sun, it's 1 AU. That's 93 million miles. And so here in January, we're going to look at this group of stars over here. And this is our line of sight right here. And we're looking at these stars and we see something like this, okay? The star we're interested in is the one right above my pointer here. We want to know how far this star is away. We'd like to know this distance. We know this distance, and this is the distance we want to find. What we're going to do is actually take a picture of this star in January. Then as we go around the Earth, when we get 6 months later down here, we're going to look at the same field, but we're going to be looking along a different line of sight. Notice that. And here's the star in July, and there's the star in January. And that shift is due to the fact that we have moved around the orbit 6 months around the sun. Now, we can actually measure that angle, okay, and that angle is twice this angle, okay? So once we know this angle and we know this distance, simple trigonometry can give us this actual distance. Now, this is a very powerful technique. It used to not take us out very far, but nowadays this technique can be used with satellites very far out into the galaxy. So when something is close enough for this technique to be usable, it always is used. Obviously, when this star gets farther and farther and farther away, what happens is this angle gets smaller and smaller and smaller and smaller. And when the angle finally gets too small that we can't observe it, that means this technique can't be used anymore. So that's the actual limitation of parallax. Now, in general terms, we can do the distance thing without using angles by simply noting a few things. We talked about apparent magnitude before. This is an old friend of ours, as a matter of fact. And this is simply the brightness that something appears to have in the sky. This is what it appears to have. The reason we like small m, or the apparent magnitude, is we can observe it. And as soon as it gets dark, we can open up our dome, attach our camera, take a picture of the star, boom, we've got the brightness of it. That's what we mean by apparent magnitude. Now, the luminosity is trickier because the luminosity is an intrinsic property of the star. It is the energy per second coming off the star. Engineers would call that the power of the star, but we'll just simply call it the energy per second. And by the way, the absolute magnitude, which is defined as the brightness if all stars are moved to 10 parsecs away. And by the way, a parsec is 3.2 light years, okay? So this is another distance unit that astronomers like to use. The absolute magnitude is actually directly related to the luminosity. So when we can plot either one or both, as you'll see, and everything works out. Now here's the trick. Are you ready? If you know the luminosity or the big M, they're basically the same. And if you also know the apparent magnitude, which remember we can always get because that's the brightness in the sky as it appears. So all we really need is the luminosity in addition to the small m. We can actually calculate the distance d. The reason is the luminosity is how much energy is really coming off the object, and the apparent magnitude is how bright it actually appears. So when you mathematically compare how bright it appears with how bright it really is, that tells you the distance, just like that. Very powerful technique. It's used all the time. We'll tell you more about that downstream. Now here is a very important thing called spectral classes. I actually took this right out of the text because this is an important concept. Stars are divided into spectral classes. Notice O, B, A, F, G, K, M. O's are the hots. Notice the temperature. M's are the cools. Notice the temperature. The sun is a G star. And as it says, sun's a G2, and that's about 6,000 degrees, okay? Now, the reason this is important is that just from looking at the patterns of the spectral lines, this is a technique that was invented about a century ago, a long time ago. Very powerful. People notice that spectral lines in stars come in patterns. I showed you a little bit about that before, and they notice the patterns, if they're properly interpreted, can give you the spectral type, and that gives you the temperature of the star. This is another way to actually get the surface temperature. Remember before we had a technique based on the wavelength of the maximum intensity of the starlight coming off. This one is different, although it should give you the same temperature, and based on strictly on spectral lines. You need to know what these spectral classes are. You should read about it in the text and make sure you understand what it is. And here are some actual real stars that are in all of these spectral classes. By the way, the O stars are the ones that are big enough to actually go supernova. None of the other ones can do that. All right, this is the great secret. This is where the great secrets about stars are hidden, but not too much. This is called the HR diagram. It's named after two guys, Hertzberg and Russell, who designed it independently. And what you need to know is that the HR diagram is always a plot of luminosity, and in this case, they're calling it intrinsic brightness, but that's what the luminosity is, the intrinsic brightness, and it's usually given in sun units. That means that right here, all the stars on this line have the same luminosity as the sun. And you can see the sun is on that line. But notice, if you go way up here to the top, there are stars that actually have 1,000,000 times the luminosity of the sun. That means that they're 1,000,000 times as bright if you're at a comparable distance. And imagine if you woke up one morning and the sun had risen, but instead of being the regular sun, it was 1,000,000 times brighter than what you're used to. Of course, you wouldn't be alive for very long because it would take out the Earth, and it wouldn't be a very pretty picture. Notice that some of the dimmer stars go down here to 1,000th of a solar luminosity. We need to look, and what's plotted along the x-axis is the star's surface temperature. We have two techniques for measuring that we've talked about. But notice the funny thing about the surface temperature in this diagram. The surface temperature increases to the left. Notice that? Here we are at 2,000, here we're at 40. So it's not like a normal graph, which increases to the right. That's all you have to make a note of. And this makes the special patterns that you see up here, which are very dear to astronomers, and hopefully you'll grow to like them too. Here's one of the basic regions. It's called the main sequence. That's because it is the main sequence. Now, the sun is on the main sequence. But here's what you need to know. All the stars in the main sequence are burning hydrogen in their cores. Burning hydrogen in their cores. That's not true for these other stars over here, and it's not true for these stars here. The stars that are burning hydrogen in their cores and are stable are called main sequence. Here's the sun. Here's Altair. Vega is a bright summer star. And Spica is in Virgo. These are very well-known bright stars, by the way. Now, here's another arena inside the HR diagram. These are called white dwarfs. Make a note of this. White dwarfs don't burn anything. They're just cooling off. This is kind of a cemetery for sun-like stars. Someday the sun will be down here. White dwarfs are usually about the size of the Earth. Remember, these are former sun-like stars that have gone through their life cycle, burned up all their fuel, all their hydrogen and other things if they can burn them, and wound up down here. And notice that this corner is dim, but it's very hot. So that means that these stars are not giving off a lot of light, but they're very hot. And the only way that can be true is if they're small. And remember I told you they're Earth-sized. Notice the stars over here are cool and dim. Cool and dim, these are called red dwarfs over here. The stars up here on the right are cool, but they're bright. These are called red supergiants. The most famous one of those is called Betelgeuse. And there are others, of course, as well. Here's the red giant category. This is where the sun will wind up when it runs out of hydrogen in its core. It'll become a red giant. It'll grow to about 100 times its current size. It'll suck up the two inner planets, Mercury and Venus. It may take out the Earth too. It's not clear yet. It's hard to tell in the computations at this moment. But anyway, these stars here, some of them will go supernova. That is, they will explode. Betelgeuse certainly will. This is a star in Orion that's famous for being variable. And people thought it was going to blow up recently, but that was unlikely. The odds that that'll happen in your lifetime are small. So make sure you understand the basics of the HR diagram that I just explained to you. In the upper left, we have the bright and the hot objects, okay? And notice, even though these objects up here are very bright and very hot, and these ones down here are very dim and very cool, they all burn hydrogen, which means that in their cores, they at least can get the temperature above 10 million degrees, which is the ignition temperature for hydrogen that wants to go through fusion and generate energy in the cores of these stars. The other thing is the mass of the stars goes up as we go up to this portion of the HR diagram, the upper left, lower right, these are small stars. Okay, now here's another thing called luminosity classes. This is simply a language for stars that are bright in some cases. These are the so-called bright supergiants, 1A, 1B, 2 bright, and the giants are 3. The subgiants are 4, and the main sequence stars are 5. This is just a code for these names. You can check this in the text too. Now, here is something you should remember. The most important parameter for a star is the big M, friends, mass. Okay, if you know the mass of a star, you know almost everything about it. You know how long it'll take to reach the main sequence. That's when hydrogen starts to burn. You know how long the star will stay on the main sequence. By the way, the sun will stay on the main sequence for 10 billion years, but many other stars will not. They'll be there for much shorter times or much longer times. So the mass also tells you how the star is going to die. If the star is going to become a supernova and blow up, that means the star will have to be at least 8 times the mass of the sun. Okay, so the sun isn't even close to that cutoff. The sun will never become a supernova. I don't know if that makes you feel better or not, but it'll die in a different way that we'll talk about later, as a matter of fact. Now, for single stars, that is stars that are not in orbit around some other star, there isn't any real direct way using gravity to measure the mass, which is unfortunate. We can do it in indirect ways, but it's not as precise. For a binary star, we're basically dealing with 2 stars that are orbiting around their center of mass. And if we watch the star long enough and we measure the time it takes these stars to go around each other, that's called a period, and we measure the distance of the stars are apart, we will be able to actually calculate the masses of these stars. So that's what you need to know. Binary stars are particularly useful for computing masses. And why do we care? Because this is the most important parameter about any star. All right, here's the last one. This is a star histogram. This is a great diagram. This is actually, if you look closely, this is actually an HR diagram. But notice what they're using here is spectral types. That's why I wanted you to be sure that you know what those are. The O's are the hottest, the M's are the coolest. Here's the sun with G's down in here. They've got it down here as well. And they insisted on using, this is the only bad thing about this diagram, they insisted on using absolute magnitudes. Just think of this as being the luminosity of the star. It's the same thing. Remember, magnitudes get bright when they get very small. So -10 is a lot brighter than 0, and +15 is a lot dimmer than these numbers up here. Luminosities are a lot easier to look at because they just give you the in solar luminosities, it tells you immediately how bright the thing is. But first of all, this is telling you that the height of these skyscrapers is telling us the number of stars of each type that are actually in the galaxy. So what's the most common star? It's red dwarfs. Now, when you go back and look at red dwarfs, you'll see that these are cool, dim, main sequence stars. That means they're stars that are burning hydrogen like the sun, but they are much smaller, they have much lower mass than the sun, and yet they're very common. So, and they're very common throughout the galaxy. Okay, that's the whole point here. Now, notice the big stars way up here in the upper left of the main sequence, and the supergiants are so rare that they don't even make a building. They don't even make a skyscraper at all. And that's telling you about how the galaxy works, because these big stars are the stars that create the heavy elements, the elements like silicon and iron that make up Earth-like planets, and the elements that make up complex forms of life, such as carbon, oxygen, nitrogen, and so forth, that you find in complex forms of life. And the sun is right about here. What's interesting is the white dwarfs are quite common in the galaxy. And remember, these are stars that are not burning anything. This is a stellar cemetery for sun-like stars. And that's, of course, why there are so many of them, because there are a fairly large number of sun-like stars. When they die, they all go down here into the white dwarf area to live, or to whatever they do in cemeteries. Okay, so there you go.